Start this. Happy leap day. Crazy. Let's see here. So last day, usually I do review, but then I ended and said, well, that's just theoretical. In application, we're just going to use these formulas. And so it's important to know where we're getting things from, obviously, but ultimately for our applications, which is what you're going to be tested on, not terribly important. So what we developed last day was the proportion. So the sample proportions come from a population that's normal, which is kind of cool. Scratch that, very cool. Because the sample proportion comes from categorical data, and then all of a sudden it kind of evolves into a normal distribution. If you have enough sample proportions, which is what you're doing in the lab, is just looking at, okay, what if I have 100 sample proportions, then how do those behave? And then we said, okay, so we know the shape, it's going to be centered on P, but we don't know P. So then we say, I'm going to use my best guess, which is P hat, my sample proportion. And then I have a spread of the square root of P hat, Q hat, because I don't know P still, over N, and that's going to be called our standard error. So in terms of review, I just want to review some notation before we kind of get started here. And maybe I'll, put it down here. P hat is a sample proportion. A sample proportion. It's our point estimate of P, our population proportion. And we also said that, or I can't remember, I feel like I said it just briefly, that it's going to be X over N, where X is the number of successes, right? And so where X is the number of successes. Is it hard to read the green in here? I'll change it to blue. Ta-da. Okay, what else did we have? We said, okay, then the standard error. Wait, I need a pen for that to work. The standard error of P hat. And I guess if you skipped, because you've got tests this week, and I know you do, that's totally fine. It might be a little bit, what's going on here? The standard error of P hat, Q hat over N. This is going to take the place of our standard deviation. It's the standard deviation of sample proportion, which is why we adopt new terminology. But this is really the spread. I keep trying to use the green, but I guess it's not going to work here. Orange works. This is the spread of P hat, right? It's going to take the place of the standard deviation in the normal distribution. Oh gosh. Okay, hang in there, everyone. All right, so now we've got all these components, remembering, right, that Q hat, I probably made a big deal about it. I honestly can't remember, but Q hat is 1 minus P hat. I want to highlight that you're absolutely welcome to use 1 minus P hat, but you'd have to put brackets around it. You'd have P hat bracket, 1 minus P hat, end bracket, and I'm just lazy, so I write Q hat. And whatever you want to do is fine. I know what you mean. If you want to do 1 minus P hat, just to eliminate kind of some some terms. But if we scroll to our formula sheet, right, this is the section that we're in. We're We've just got one sample and we've calculated a proportion from it. And today we're going to work on just the confidence interval. Next day, we're going to work through hypothesis testing, which is the formal testing method that we use in statistics. And then we finish on kind of a fun little sample size calculation, but we'll leave that for last. Could do it today, but I ran out of time this morning, so I know I'm going to run out of time in this class too. Okay, so we've got this confidence interval, and we talked about just in general what a confidence interval is last day. We said, okay, I have my best guess, which is my p hat. That's my best guess for p, my population proportion. That's all I know, okay? And then what we said was, okay, usually I don't just give my best guess, I give some bounds on it, right? How far is it to my house, for example, right? 5 kilometers plus minus, I don't know, a kilometer, not really sure, right? And so then we do that plus minus, and that's exactly what we're doing here, right? Plus minus, and then today we're going to talk about this chunk, okay? Okay. So, confidence intervals, this is section 5.2. Confidence intervals for a proportion. A confidence interval gives us a plausible range of values for this population parameter, and this is in general, okay? And we call it a confidence interval. And so using a sample statistic or a point estimate to estimate a parameter, usually we liken it to fishing with a spear, right? You see a fish and you try to jab it, right? And so that's fine, I guess, but you're more confident in catching this fish, right? If you use a net. And so the confidence interval is the same as using this net. And so using just your point estimate, your p hat is the spear, but then we put a confidence interval around it, and then we have this net. Now it's very important to recognize that the population proportion, which we're trying to capture, the fish, right? It's fixed. It exists. We don't know what it is. We're trying to capture it. And so it's not moving around or anything. I guess that makes the fish example a bad example, but it's just sitting there. It is there. It exists, but we don't know exactly what it is. Yeah. And so, right, if we report the point estimate, which in this case is going to be our p hat, right? We probably won't hit the exact population parameter, which for this scenario is p. Notice how this is general. And that's because the confidence intervals, we're going to be able to apply these same concepts to any confidence interval that we want to build. Okay. And so, so we probably won't hit the exact population parameter, but if we report a range of plausible values, then we have a good shot at capturing this parameter. Now, you have the slides, and the slides do just kind of outline the answers, but what I want to do is, or what I'm going to do, I can't talk over you guys, sorry. I can't. And so what I want to do is just go through this example, and I'm not going to use the slides. We're just going to write out all the work and all the things that I want to talk about, because I'm stuck in my ways and I have my own ways that I want to introduce these things. So then you'll have the slides and they'll outline all the information as well. But but we'll be writing quite a bit today. Okay, so the example that we're going to be using is this one. So most commercial websites, social media platforms, news outlets, online retailers collect, I don't like this typo, collect data about their users' behavior and use these data to deliver targeted content, recommendations, and ads. We're all aware that this happens. And so to understand whether Americans think their lives line up with how the algorithm-driven classification systems categorizes them, Pew Research asked a representative sample of 850 American Facebook users how accurately they feel the list of categories Facebook has listed for them on their page of their supposed interests actually represents them and their interests. Now that's a long blurb, and there's some key information here that I want to highlight. Okay, and so here, first off, they asked a representative sample. Representative, we talked about last day. Well, so of course our sample has to be representative of the population that we want to talk about. I'll put a little asterisk up here and maybe green one here. Representative in this case means that, oh, well, I don't have that many colors to choose from. I'll use green for the not so important ones. Sorry. I see that it's hard to see, but I don't have very many options. So if it's representative, what does that mean? It means it was randomly selected, presumably, right? And so randomly selected. Okay. 850 is going to be our sample size, right? They collected a representative sample of size 850. And so here we have our N is 850. Right. Now, this next part tells us what population we're working with, American Facebook users, right? That's a subgroup of all Americans, right? And so now our conclusions only apply to this population. They only apply to American Facebook users. That's okay if that's who we want to talk about, obviously. It's a problem if we want to extend it to all Americans, right? But it's okay if we want to just talk about Facebook users, which makes sense because we're talking about how do you feel about Facebook's categorization of you. Makes sense. And so here, our population is American Facebook users. So a lot of information in that little blurb, right? Or not so little, because then they just go blah, 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 blah. Okay. So then we're given that 67% of the respondents, so of the respondents, right? This makes it a sample proportion. Okay. So this tells me that this is going to be a sample proportion p hat of 0.67. Now it's important. So p's, which are what we're dealing with, are proportions, which means they have to be between 0 and 1. Often we report proportions as percentages just because they're easier to read and a little bit cleaner. But you have to convert them to decimals right away in order to do any math. So now this is our point estimate, our best guess at how the general population of American Facebook users feel. We understand that if I took a completely new representative sample of 850 American Facebook users, this would change. Probably not drastically like we established last day, but there's variability there, right? And that's where the standard error comes in. And so 67% of the respondents said that the listed categories were accurate, which is definitely me. Well, sometimes I'm like, hey, why did that show me that? But most of the time it's bang on. Estimate the true proportion of American Facebook users who think that, another typo here, it's not important, but it's annoying to me, that Facebook categorizes their interests accurately. Usually what I would do is I would phrase this question more explicitly. And so what I want to do here is just add a page so I can show you what it's going to look like. How can I get lines on here? I don't know. I don't have my usual, maybe here. No. Sorry, I'm guessing you can't see what I'm struggling with. That's okay. All right, no lines for me. That makes a mess for you. If I just copy this, I would say usually, fine. Always, when I ask a question, I'm going to ask you to construct a confidence interval explicitly. Okay, so I want to show you what that looks like. And so usually, well, always in our case, I will ask you to construct a confidence interval which I'm going to pretty quickly abbreviate to CI because it's annoying to write out, a confidence interval explicitly. So instead of this, so instead of saying estimate, you can ignore this. I'm going to say construct a 95% confidence interval for the true proportion of American Facebook users who think that Facebook categorizes their interests accurately. Ugh, right? But what is it saying? I'll write it down, but just before I do, let's talk about what it's saying. The true proportion is the population proportion, right? And so the population proportion of, well, the population that we're interested in or that we drew from, American Facebook users. And then what are we talking about? The proportion of what? Who think that Facebook categorizes their interests accurately. So it's wordy and it's long, but really what I'll show you is that you're just going to reword this as an answer, right? And so you just steal this and it makes you sound really clever. So instead of this part, I would say construct a 95%. Now today we're going to introduce other confidence levels, 90, 98, blah, blah, blah. We can do any confidence level that we want, but default is 95%. Okay, and so we'll start there. Construct a 95% confidence interval for the true proportion of American Facebook users who think that Facebook categorizes their interests accurately, right? And so I would explicitly say, make this confidence interval. So you don't have to dig around for it. I find that when it says estimate, which we are doing, right, by building this interval, but it's kind of hidden and I don't like that. Okay? So for us, it'll always just say, make a confidence interval. Okay? And I have to tell you what confidence level, right? And I always will. Okay? In life, though, the default is 95%. Okay? All right. So let's see here. If we go to, wait. We go to the formula sheet, and I'm going to erase this just temporarily. Copy. There. If I see a question that asks me to construct a confidence interval, right? As long as I've identified what type of question it is, right? If you scan your formula sheet, kind of looking to the future, right? You'll see that there are confidence intervals in almost every section from here on out. So you have to decide what type of question you have, right? And then pick the confidence interval in that section. But once you're there, right, this is what we have to do. We build a confidence interval for P, the population proportion of American Facebook users and blah, 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 blah. Okay, let's talk about things we know. We know what P hat is. P hat is our sample proportion. In fact, we already know that P hat is 0.67, right? And so let's just say we're already given P hat is 0.67. We know that. Oh man, I gotta stop using. But I have an internal color scheme, maybe dark green. That's what I should be going for. That's better. And don't worry, my internal color scheme doesn't really make sense either. So P hat is 0.67. Well, we're going to tackle Z star today, right? But let's just introduce that Z star is called a critical value. Oh, that's pretty good for now. How about this? How about we add a little piece? What does a critical value do? The critical value tells you how many standard errors to move out for a desired confidence level. So the critical value can I say tells you? It's not very official. Tells you how many standard errors we have to move out from P hat for a desired confidence level. We have to move out for a desired confidence level. Okay, kind of cryptic for now. Maybe, maybe not. We know from last day that this huge thing is the standard error, right? And so we already know, hey, where's that green that I had? Maybe I'll replace this green with the dark green. And we have, let's say, oh, let's do Q hat first. Therefore, Q hat is 1 minus 0.67, which, so Q hat is 0.33. Right. All the Q's are just 1 minus that P, right? Q hat is 1 minus P hat. Q is 1 minus P. Q star later on is going to be 1 minus P star, right? But I use it to save some writing. And we also have N is 850. We know from last day that the standard error of P hat is this square root of P hat Q hat over N. That's how we find the spread of P hat, right? Which means that this huge blob is the standard error of P hat, right? Or generally the standard error of whatever the point estimate is. Okay? So you have a point estimate, it has some spread. You want to move out some critical value. Okay. And if you had to take a guess, what if we wanted to make a 95% confidence interval? Remembering that we have a normal distribution from the central limit theorem. We haven't checked the conditions yet, but we will, and they will be satisfied, so that's fine. What would your Z star kind of gut reaction be? Probably 2, right? 68, 95, oh, that sounds pretty good. 99.7 rule, all right? So going back to that empirical rule. So then gut reaction would say, I should probably move out 2 standard errors from my point estimate, right? We're going to get a little bit more precise. Spoiler alert, we should use 1.96. Is 1.96 that different from 2? No, right? But we're going to try to be as precise as we can for the most part. And so how would we find the more precise value of a critical value? So here, I'll say from the 68, 95, 99.7 rule, we suspect that Z star for a 95% confidence level would be 90 or would be 2. Oh gosh. We suspect Z star, which is the critical value, we suspect Z star for a 95% confidence interval is 2. Right, from drawing this normal distribution, Z is centered on 0. And if I move out 1 standard deviation, 2 standard deviations, but now we're moving out standard errors, but they behave the same way because we have a normal distribution, right? 95%, Z equals -2 and Z equals +2, right? Because Z has a standard deviation of 1. Now we're just plastering that onto our spread and moving out that amount. Okay. And so this is where we get the plus minus from, right? You go down a little, you go up a little. And so in our interval here, this is where we get our plus minus Z star from, because you go down and up the same amount, right? Because it has to be symmetric. Okie dokie. How can we find a more precise value for Z? So here, I'll say we will use a more precise value of Z. Well, of course, you could use Excel very easily, but not on the test, unfortunately. I wish we could. But so we'll use a more precise value for Z star. How would we get there? Okay, we know how to do this. Man, it's almost like we did all that work leading up to something, huh? Oh, crazy. What if we did this? I'm just going to replicate what I have up here and forcing 95%, bless you, here, which translates to 0.95, right? An area of 0.95 in the center, meaning I have 0.05 split evenly in the tails. So then from here, I have 0.025, and from here, I have 0.025, right? Because it has to be symmetric. Now what can I do? I can use my Z table, right? And figure out, well, what value of Z makes that happen? Then I'm going to leverage the symmetry and not do it again. You can to confirm it, but you don't have to. And so let's go to your Z table. Oh, I don't, have it here. Okay, so we've got our Z table. We're looking for a table entry, right? An area to the left, which is what the table gives us, of the closest thing to 0.025. Don't be distracted by these 0.00. That's too small, right? You want to go for the 0.025, which, well, can you believe our luck is actually on this table? Usually it's not, right? We're used to it not being on the table. And so here, what we're going to do is we map this back to the Z that makes that happen. I am going to nab this and bring it in. Oh, I need more room. Like I said, we're going to do a lot of our own writing today. I'll zoom in here, but hopefully that's big enough when I make the PDF. Okay, so we found this table entry of 0.025. Exactly, we're so happy. And now I can figure out the Z that makes that happen is negative 1.96. Aha. So now we say Z is negative 1.96. Just mapping that back. Like I said, is that far off from -2? Not really, right? It's just a little bit more precise. It's just good to be aware that there are more precise values. By symmetry, this one has to be plus 1.96, right? And so now I've got Z is 1.96. To encapsulate that plus minus, I'm going to just summarize that as Z star is 1.96 because I've got the plus minus in the formula. So therefore, Z star is 1.96 for a 95% confidence interval. Okay, now that you know how to do it the hard way, how about I show you how to do it the easy way? So that's where the new table today comes in. It's this one, it's single-sided, fun. So if you don't have one, you can come up and grab one, or I'll bring it up on here too. So for the most common confidence levels, we can use the t-table. So a new table, we can use the t-table to find Z star. Now, with this method that we just developed, you can find any confidence level, but I'm not going to make you do anything that's not on the t-table. And so that's why I want to show you this shortcut, because it's going to save you a bunch of time, right? You know how to do it. You know what it's doing, right? But now this, so in the tables that I posted, I'll erase this. You've got the negative side of the Zs, you've got the positive side of the Zs, and then you've got this table C, the t distribution of critical values. Now I'm going to copy this in so we can have a look at it. Maybe I'll just do that. And we're going to be ignoring a large part of this table until chapter 7. But by then we'll be familiar with the table and it won't be so bad, right? And so for us, we're going to ignore the degrees of freedom until chapter 7, which is the bulk of the table. right? So ignore until chapter 7. Oh, there you go. So if we're ignoring the top part or that part, oh, maybe put this down here. More tables. But that's it, I promise. Can you imagine if I had given all these tables and things to you on the first day? Y'all would have dropped out, I think. Oh no, I'll wait. I'll wait till it gets better. Well, it doesn't get better. Marking would have been less though. So maybe that's where I'm going wrong in my strategy. Oh. So here, this continues. You've got this table, and the only part that I'm interested in, hey, this looks familiar. Z star. Okay, what does that link up with? Well, here, I see the 1.96 that we just found, and what do you know? It's attached to a confidence level of 95%. Okay. So from here, we have a list of, and maybe I should squiggle this part out as well. Next week, we will be using this part. Okay, and so that's why I'm not squiggling it out quite yet. But for now, we're going to be working with these confidence levels. Okay, construct a 90% confidence interval. What's your Z star? Well, it should be 1.645. If you went to the table, what would you probably be doing? You'd be choosing between 1.64 and 1.64 or 1.65. Well, it should be 1.645 because it happens to be right in the middle. What if I make you do a 99% confidence interval? 2.576 is your Z star. So now you have this shortcut for finding these confidence or these critical values. Okay. And so if we think about our, maybe not 68, sure, 68, right, is close to 70. It's not on here, but 68 is close to 70, which is close to 1, right? 95, well, 95 is 1.96, which is close to 2. And then 99.7 again isn't on here, but it's close to 99.8, which is very close to 3.091, right? So that's where the 68, 95, 99.7 rule comes from. In fact, we could, and I have taught this course before, well, it was the similar course, but kind of higher level, but with just the 68, 99, 95, 99.7 rule, because you can estimate the areas and then you just use software if you want to get more precise. Anyways, that's not for us. So, but you can, yeah.
On the last question, you used the like 0.025 the Z table value.
Yeah.
Where'd you get the 0.025?
Oh, so here, I'll go back there. So if you want a confidence level of 95, then that has to be in the middle. And so then 95, then you have 0.05 left over, but because it's in the middle, it's split evenly between the tails, right? So you don't have to do this anymore if you prefer to use the shortcut, right? But I just wanted to show you that you know how, but there's also a shortcut. Yeah. All right. Hey, so that's pretty good. So just remembering that, okay, the Z star that I find tells me how many standard errors to move out to hit that confidence level. Okay. All right. Now, where was I? There's a lot of ins and outs, aren't there? Well, I guess I make it so. Now, what about checking the conditions? So the reason that we're able to use Z star is because we're assuming it follows a normal distribution. If it doesn't follow a normal distribution, Z star doesn't apply, right? And so we have to check the conditions. So before we can even build this interval, which I think because you guys are usually quite mathy, probably okay with just, you've got all these values, you're ready to find this interval, right? You can do it, but we have to check the conditions first, okay? And like I said last day, to check the conditions, it's a lot of brain space. So there are some key things to remember, and then it'll just be check boxes. Check all that apply, right? And then you just tell me which conditions you should check. And so in order for the central limit theorem to apply, we must check the conditions. Okay, what were the conditions? The first condition is independence, right? All our observations have to be independent of each other. There are two things that we have to check in order for that to be satisfied. So the first thing is independence. The number one thing, if you completely blank on the conditions, you always check it has to be randomly selected, right? The random selection ensures that these observations are independent of each other and representative of the sample, right? So the number one thing is that it's random, and I'll highlight it because that's the most important one. Okay. Now, let's go back to the question, which is quite a scroll up, I guess, but we did talk about it just briefly, right? It didn't say that they randomly selected a sample. Often it'll say a random sample of 850 American Facebook users was selected, and then you can just say the sample was randomly selected. Here, we have to go about it in a slightly different way and say, we assume the sample was randomly selected, right? It either was, or we have to assume that it was. Now they tell us that it's representative, and so I feel confident assuming that it was randomly selected, right? And so how we're going to phrase this here is we assume the sample was randomly selected. That's good. Easy peasy. The second one, that's optional because it's usually just as ridiculous as we're about to see here. This one's optional. The n less than 10% condition says that, okay, in order for all these observations to be independent of each other, it's important that you haven't sampled too much of the population. And we draw the line at 10% of the population. And so 850 Facebook users is reasonably less than 10% of, or sorry, American Facebook users is reasonably less than 10% of all American Facebook users. And so we just say that 850 is less than 10% of the population of all American Facebook users. Even with that subgroup, I still feel fine about it. So usually it's just as ridiculous as this. That's why it's optional. You don't have to remember it, but it's just good to, what's my job to show you all the things and then tell you what's optional for me. Okay, so that's the first chunk of the conditions. The next chunk of the conditions is what I call the normality condition or the sample size condition. We need to have enough of a sample size or a large enough sample size in order for that normal distribution to appear. So the next set of conditions is the normality or the sample size, or you could also call it the success failure condition in this case. But I'm going to call it the normality condition, because that way it's generic enough to apply to all the confidence intervals that we're going to do. Yeah. So the normality condition, I guess sample size also works, but the normality condition says that, okay, I have to have at least 10 observed successes in my sample and at least 10 observed failures in my sample. Okay, so at least 10 observed successes in the sample, right? I'm going to underline the observed, mostly because later in hypothesis testing, we're going to be talking about the expected successes, which is just slightly different. And hence, it's a lot of brain space for not very many marks. So don't waste your time on it. But if you can remember some key things, that's good. So you have to have at least 10 observed successes in the sample. Now the observed successes is your X, right? So if your problem gave you X, then you can just make sure that it's more than 10, which it will be, and then you're good. For us, we were given P hat. P hat was 0.67, and P hat is calculated as X over N. And so 0.67 is X over 850, which means that X is, I'm going to do the 850 on the outskirts, times 0.67, only because I like to have the decimals in the brackets. Quirks. 850 times 0.67 is 569.5. So what happened? Obviously, we didn't have half of a success, but presumably this 0.67 has been rounded, and so it's okay. I'm just going to leave it as 0.5. Okay, that's totally fine. We're just checking the conditions. Yeah, 569, whether it's 569 or 570, it's still more than 10. It doesn't matter. And so here, this is greater than or equal to 10. So that's good. So here in general, X is N times P hat. So notice, depending on what information you have, sometimes you're given X and N and you can calculate P hat, right? Or I give you P hat and N, like in this example, and then you can find X relatively easily. All right. What's the second part? Well, it's the flip side. I have to have at least 10 observed failures in my sample. Now, easy enough. Observed failures in the sample. How do I calculate my number of failures? Well, if I had 850 total and 569.5 of those were successes, then the remainder must be failures. And so what you're going to do is you're going to do N minus X, which in this case is 850 minus 569.5. I get 280.5, oops, 0.5. Not sure where that came from, which is greater than or equal to 10. I've checked the conditions. They're always going to check out, right? Because all our problems are all doctored and you know, they're always going to check out. So that's not the concern. It's just knowing to check them when you're out in the real world, because then things aren't so so nice. But usually they do. Observed failures. So now we've checked the conditions. We have made the argument that all these conditions have been satisfied. And so therefore, the conditions for the central limit theorem, the CLT, are satisfied. Now we can build a confidence interval. So P hat plus minus Z star times the square root of P hat Q hat over N. We know that P hat was 0.67. We already found Q hat was 0.33, right? 1 minus 0.67. We know that N is 850, and we just established that Z star for a 95% confidence interval is 1.960. I keep the 0, you don't have to. I think it makes it look nicer though. Plug and chug. Here we go. So P hat is 0.67 plus minus 1.960 times the square root of 0.67 times 0.33 divided by 850. Nice and slow. BEDMAS still applies, right? And so, well, still applies, always applies. 0.67 times 0.33. Just for the first part, I'll just write out every single part. I'm obviously not going to do that every time, but just to remind you of the BEDMAS order of operations. Or maybe you're used to PEMDAS. Are we a BEDMAS crew or a PEMDAS crew? Or something else? Order of operations. It's not for us. Do you know what I mean when I say BEDMAS? BEDMAS? Okay. In the States, I think they use PEMDAS. Parentheses, exponents, multiplication, division, addition, subtraction. So 0.67 times 0.33, that's our first step, right? We need to multiply this, the numerator before I can, well, doesn't matter because multiplication and division are in the same level, but just for simplification, I'll do the multiplication and then the division. And so 0.2211 divided by 850. Of course, you can skip to the very end if you want. But like I said, I just want to show you. Sometimes it's been a while for order of operations. So this becomes a very small number and it gives it to me in scientific notation. So I have to think about it a little bit. 0.0s, I have to move my decimal, boom, 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 boom. 26011764771. Now, I want you to keep all your decimal places, but I do not want you typing in this every single time. That's crazy. And so make sure that you're familiar with the store function on your calculator. The financial calculator has a really nice store function, but any calculator has, or any scientific calculator has a store function, right? So that you can store it and then pull it back up and keep all your decimal places. But you've probably taken business math and already know. Okay. Next thing, square root. I have to take the square root of that thing. 0.67 plus minus 1.960 times 0.01612816316. Or you can just tell me where you stored it. If you want to show this work, you don't have to, but you can tell me where you stored it, and that's fine. What is this value? That's the standard error of p hat. That's the spread of p hat, right? And so this is the standard error of p hat. It's essentially your standard deviation, right? So you can think of it as your standard deviation. And then when we multiply it by 1.96, we get times 1.96, we get 0.67 plus minus 0.03161111998. Probably keeps going, but who cares? This chunk is called the margin of error. Now, if you're reading research papers and things like that, they would report the margin of error and tell you the confidence level that they used. And from there, you can reverse engineer it, right? From here, if you know Z star, you can find the standard error, right? They don't usually report it, but you can find it. So this is called the margin of error, which depending on your field, they call it MOE or ME. But for us, on our formula sheet, I have little m. So what we're going to do next week, because we won't have time today, is say, well, what if I go into a study and I want to force this to not be 0.0316? What if I want to force it to be even tighter, right? 0.02, 2%. Right, this is 3.16%. I want to narrow my interval down to be more precise. Right, what if I want to force it to be 2%? What could you do? Well, you could say, well, the only way I could do that is by increasing my sample size. Right, the only way to narrow an interval now is to increase my sample size. So then the question becomes, well, what should my sample size be? So then you can force this value to be 0.02, and then you can work your way backwards and solve for n. I give you the formula on the formula sheet, but that's what we're going to be doing. So that's kind of fun. That's a way of finding the sample size that you would need. Okay? But that's for next week. For now, we're so close to having an interval, right? So from 0.67, I want to go down 0.0316, blah, blah, blah. And then I want to go up 0.0316, blah, blah, blah. And so now how we report our interval is in round brackets, mostly because we're going to be rounding our values. And yeah, I never thought of that. The round brackets, the square brackets are exact values, but you can use round brackets if you've rounded your values. Do you know how many sections of pre-calculus I've taught and not thought of that? It's nuts. Can't wait to tell Steve. Okay. He's gonna be like, yeah, I say that every term. Show off. So 0.67 minus this whole thing. I'm gonna store this in my calculator. So I'll store it in A or 1 or whatever you want. And then I'm going to go 0.67 minus that little guy, puts me at 0.6383888002. That's my lower bound. It's really important that you report your interval from the smallest to the largest, because when you're reading on a number line, from the largest to the smallest actually doesn't exist. Right, and so I will take half a mark off if you swap those, which I understand why it's tempting, because you've got the plus and then the minus, and usually that's how we want to do things in the order that they appear. So I understand, but it's important to recognize that the interval from the higher end to the lower end actually doesn't exist. Okay. And so I'm building habits. Potentially good habits, I don't know. So now 0.67 plus 0.031, blah, 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 blah. I get 0.70161111998. We can round these values a little bit, right? And so, or 0.6384 up to 0.7016. 4 decimal places is usually safe. What could you do? What else could you do? Well, if you're really wild and crazy, you could convert it to a percentage, right? 63.84% to 70.16%. But then your interpretation has to be in a percentage and not a proportion. But depending on how you want to report it, that's fine. So we've got this lower value separated by a comma and then the upper value in our interval. But wait, there's more. Act now, and I'll throw in a second ShamWow. Are they still selling ShamWows? I have to admit, I did buy a ShamWow once at the Peony, and it was really good.
What is it?
A ShamWow? No, you're right. Let's take a moment. A ShamWow is a super absorbent towel that was like very popular in the early 2000s. Thinking about when I bought it. And it was these ridiculous infomercials, I guess. ShamWow. And they were orange, I think. This is half the work, right? What's the other half of the work? I have an interval. What am I supposed to do besides interpret the interval? Dang it. Okay. Whenever you build an interval, you have to interpret it. It's half the marks. You can all do math. We can all do math, right? You practice it enough, you can all do the math. That's half the marks. The interpretation is the other half the marks. Okay, and that's kind of the reason that people are thrown off by stats, is because it is this song and dance between math and a lot of English and interpretation and a lot of wording that's very particular. In fact, for the interpretation, I want you to memorize this exact sentence structure. Don't put me in a cage like that, Emily. Well, until you know what you're talking about, you have to use this sentence structure, because there's so many ways that you can misinterpret it, and then I would have to take marks off. But I want you to use this sentence structure, okay? And so we, I'll say once we have a confidence interval, we must interpret it. Until you have a very, very thorough understanding of what a confidence interval is, which I'm going to go out on a limb and say you don't. Mostly because I didn't for a very, very long time in hindsight. And so I think you know, but you don't. So until you have a very thorough understanding of what a confidence interval is, but mostly what it isn't, use this sentence structure. Memorization, no one's favorite thing, but the more you do it, the better you get at it. right? And so you can start memorizing it. And the reason it's so important is because most people want to say things that aren't true, and I don't like that. You're going to use this sentence structure. I like to use a common we. We are 95% or whatever percentage confident. We are, oops, blank percent confident. Am I out of time or something? No, not yet. We are 90 or blank percent confident. The interval from blank to blank, right? From your lower to your upper, captures. Let's highlight that because that's a really important term in here. Captures, thinking about our fishing example, we're trying to catch the population proportion, right? And so we're trying to capture this thing. It's fixed, it exists, we don't know what it is, right? So it captures the parameter. Now, the blank, and here I'll say the default is 95% from the lower to the upper, and then the parameter. That seems innocent enough. But what is the parameter in this case? It's the population proportion or the true proportion of American Facebook users who feel that the algorithm correctly, blah, 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 identified their interests. But what are we going to do? You're going to take the question that I've given you, because I'll try to phrase it in a way where you can just reword it as an answer, right? And so here, this parameter, reword the question as an answer. Okay. Let's grab the question that we're answering first so that we can steal from it. Blah, 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 blah. So then, right, the question says construct a 95% confidence interval for, and then here's the parameter, the true proportion of American Facebook users who think that Facebook categorizes their interests accurately. It's a lot of writing, but it's just tedious. It's not hard, right? And so we're going to write it out following this sentence structure, right? We are 95%, because that's what we wanted to calculate. Confident, the interval from, let's see here, 0.6384 to 0.7016 captures the true proportion of American Facebook users. Now I'm just copying this out. The true proportion of American Facebook users who think that Facebook categorizes their interests accurately. At first glance, this looks very difficult, right? But if you follow that sentence structure that I gave you, then you just snag whatever it is that you wanted to make a confidence interval for, and that's your parameter. Sometimes it's long, sometimes it's not, right? On tests, I try to make it as short as I can, right? But, okay, how much time do I have? Nothing. Well, some maybe. Enough to scroll through the slides. Hey, I have some time. Well, I'll make the best of it. All right. So confidence intervals. So what I said earlier was, okay, so I have all these slides, you have them, and it just summarizes everything. But look at how quickly they got to the interval and how sloppy. We did it all together. Just for kind of, in case you want to work through it, the answer is B. The interpretation, and then we talk about what are the intervals? How about if we want to be more certain that we capture the population parameter, so increase the confidence level, right? We would have to use a wider interval, right? Going from 95 to maybe 99.7, something that we're aware of, right? I have to go out further, so I would need a wider interval. But kind of a cute cartoon. Taking a look at tomorrow's weather, the high temperature will be between 40 below and 200 above. This guy's never wrong. So he's very confident, but not very precise. And that's why the default is 95%. And I can't talk anymore. So I release you. Have a great weekend. I'll see you on Tuesday. You and me both.
Do you know what you have? Like what you have had?
No. All I know is that it wasn't COVID.
It wasn't COVID. That's like insane. I can't believe how much you've been sick. That's terrible.
I've never been sick this long. It's insane. Yeah, it's just nuts. And like thoroughly sick.
I know.
Like
Like